Do you mind being called an atom crusher?
An atom smasher.
An atom smasher, that's it.
No, I kind of like that name. I call my computer Atom Smasher because it has to have a name.
Kia ora, I'm Sharon Brett-Kelly, and today on The Detail, I'm in the presence of a great name of the science world.
Ladies and gentlemen, welcome to the Breakthrough Prize 2025. Tonight, we will be honouring and celebrating some of the most brilliant minds in the world.
Auckland University's own David Krofcheck is one of those brilliant minds. They call him the Atom Smasher because he's had a hand in one of the world's most exciting science projects, the Large Hadron Collider at CERN Laboratory in Switzerland. And at the Oscars of the science world, he and his 13,507 colleagues were recognised for this.
For 14 billion years, its existence was secret. It's been here since the beginning. Yet it remained hidden. Until 12 years ago, when scientists at the Large Hadron Collider near Geneva finally found the Higgs particle. But they didn't stop there. Since then, they've gazed even deeper into the heart of matter and led the quest for unknown physics that could explain the nature of the universe, its fundamental laws, and how it all began.
But when David opened an email congratulating him, this was his response.
Yeah, right. I won the 2025 Breakthrough Award in Fundamental Physics, right?
He was suspicious.
I thought it was a scam. I thought it was a phishing email.
Then he did start to believe.
I don't see any links asking for my bank details. I don't see anything asking for my address or my credit card number. Or maybe this is bizarre enough to be real.
Sure enough, at a who's who of Hollywood and science and techdom in an airport hangar in LA on April the 12th, David Krofcheck and his colleagues were rewarded for years of groundbreaking work.
Tonight, we celebrate 13,000 researchers from 70 countries, representing 4 experiments at CERN. Here on this little planet, they've launched the quest to explore and understand our entire universe. I believe that this quest is humanity's fundamental mission.
Today, I'm with David in his office overlooking Auckland's skyscrapers to talk about how his curiosity drives him to keep searching for answers on the origins of the universe, why he hates the term God particle, and what he thinks of Katy Perry's space adventure.
I am a senior lecturer in physics at the University of Auckland, and specialty is nuclear physics, but now it's also become particle physics.
First of all, I want to say congratulations for winning the Breakthrough Prize in Fundamental Physics, and you're sharing it with 13,507 colleagues. How does that work?
That's 13,000 colleagues. Every single one of them is required to make this happen because it's spread out over 4 major research collaborations. But it's 25 years or more of construction of the accelerator and these gigantic particle detectors. Our detectors, 14,000 tons, metric tons of electronics and detectors. It's 150 different institutes, and there are like 60 or 70 countries in the CMS collaboration. And it literally took 25 years to build the detectors, and even longer, going back, to dig the tunnel for the Large Hadron Collider. So it's like building the pyramid. It must be like building the pyramid. The Pharaoh never thanked the slaves for building the pyramid, but this is kind of like the group award for everyone who was able to contribute, building the detector, getting it to work right, taking data, analyzing the data, publishing the data, and finding new and wonderful things, at least for physics.
I was trying to work out a way of understanding what this all means and why we need to know this. And I wondered if you could tell me specifically what you are working, or even show me specifically what you're working on right now relating to this big project.
Since I do nuclear physics, I'm interested in colliding atomic nuclei. So we collide beams of lead atoms together. And you think of lead in chemistry, and we strip off all the electrons. So it's just this lead nucleus from Rutherford type nucleus. And we've stolen the technique of the experiments straight from Lord Rutherford of Nelson's technique. The only step forward is that we now have, instead of just a fixed target of lead and a moving beam, we have two counter-rotating beams of lead. And they are designed to collide at 4 different points where the 4 different experiments are. And I'm interested in cracking open the protons and neutrons that are in the lead nuclei. And interesting things come out, really parts of the fundamental matter of nature that we don't think about, but actually underlie everything else that we see around us. You and I are made out of protons and neutrons, but the protons and neutrons are made out of quarks and gluons, which glue together the quarks. These are our new table of the fundamental elements, the particles. You might remember in chemistry, you had a periodic table of the elements. Well, now we have a periodic table of elementary particles. And all of those table of elements in the chemistry table are made out of these protons and neutron, quarks and gluons. And we study how they work in nature.
So what do you see? Like when you're over in CERN, what do you actually see when you break these things open? You're going to show me.
I can show you.
Oh, good.
I can show you something that I show I use it as a teaching tool. Here's an event in which 2 protons collide. Well, let's get rid of
We're looking at a 3D image.
We're looking at a 3D image that I can rotate. And each of these different colors represents a different type of detector. So these yellow lines represent detectors that can detect strongly interacting particles. These are our protons. A high-energy proton might come out, or high-energy pi meson might come out. It's another funny particle.
So we're looking at a 3D image here, and it's the yellow part of it is like a tunnel, and then inside that is a smaller blue tunnel. But when you're at CERN, what do you actually see?
I'm sitting in the control room 4 or 5 miles away with all the data analysts, and we see signals coming from individual detectors. So I would look on my computer screen and I can see how big the electrical signals or how fast electrical signals are coming in from these particles. And we keep watching them so to make sure the rate doesn't get too high. So we're collecting so much data that we can't write it to our computers fast enough. Or suddenly the signal disappears, which is a disaster, which means somehow the beam has gone off target. This is where one of the things New Zealand was responsible for, to take care of that problem. And you watch the signal, and sometimes the signal just disappears. Or sometimes the proton beam will disappear. And that just means that a magnet is tripped off, and the accelerator lab itself, the Large Hadron Collider control room, has physically turned off the beam because they've lost control of the beam. Maybe has gone off and starts scraping the wall of the beam pipe. And that's a dangerous thing for your electronics and detectors, not for people, because this is all happening more than 100 to 200 meters underground. But we're really looking at all these individual bits of signals coming. And we'll see, oh, look, the muon detectors are working here. They're 2 muons are bending in opposite directions. They must have opposite electrical charges. So, yeah, that's interesting.
Real.
The detector's working perfectly. And we can tell this 5 miles away because of the signals coming from 100 meters underground, which go up to the control room, which is right above the detector, but then 5 miles across to where the main data acquisition area is. It's very interesting from a nitty-gritty technological standpoint, but the real physics analysis is done just like sitting here with computers.
Looking at a screen.
Or this is the paper we just worked on now. This is the PhD student's analysis.
Can you read that title for me?
That title is called Azimuthal Anisotropy of Prompt Strange D plus minus mesons at Center of Mass Energies 5.02 TeV with the CMS experiment. This is the type of thing that I studied, when it just started off when I was a postdoc.
In this immense universe, we only know one planet where matter has formed into minds. Minds that can ask big questions, like what is matter anyway? What is this planet? What is the universe?
Is there an end to this project? Or you'll
never.
You'll never know everything?
There's never an end.
No.
That's the beauty. We could be here. I'll be here. Someone else will sit in this office, and hopefully the department will have the wisdom to hire another nuclear and particle physicist and continue on looking for something new.
And apart from knowing what happened immediately after the Big Bang, how does all of this apply to our lives now?
I can give you two answers to that. I can give you the answer of why I'm at a university instead of in a private industry. And that's just, I want to know what happens. It's just curiosity. And we have the technology and the brains that have somehow evolved to ask questions about things that are beyond our immediate reach. Like what happened in the early universe? What happens with atomic nuclei? How are they bound together? How do these quarks and gluons actually work to bind together? And I love seeing the advancing story of more and more things fitting together. And so then you can make predictions as to the way stars might behave, for example, or black holes might behave, or the matter around black holes might behave. And we need this knowledge generated from accelerators on Earth. But it gives us a grasp of the bigger picture of what's happening in the universe and how our matter came to be stable and how we got to have our kilograms in our body, how mass is generated, because if mass wasn't generated, all the particles of nature would be traveling at the speed of light, and they would never be bound together into protons and neutrons. Something had to slow them down. What slowed them down? Well, this Higgs field, which produces Higgs bosons. So it's a pure curiosity from me.
And this quest, driven by pure curiosity, has improved all of our lives. Particle accelerators designed to probe matter at subatomic scales have led to medical imaging tools like PET and MRI, new cancer therapies, advanced information technologies that benefit billions.
Amazon's Jeff Bezos is talking there about how this high-end physics can be applied to our daily lives. Even though he was working on a Nobel Prize-winning project, David knew he needed something else to get New Zealand government funding. That's where Canterbury father and son team Professors Phil and Anthony Butler come in. Working together with David, they've applied the same technology used in the hunt for the Higgs boson to invent the world's first 3D colour X-ray.
And I thought, okay, if you can work on an applied project like medical imaging techniques using detectors that were developed for this curiosity-driven science at CERN, use the electronics, which are super fast, and radiation detectors, which are super sensitive. If you can build an X-ray spectrometer, an X-ray device to measure characteristic energies from the atoms in your body, then you get something that's not just a black and white traditional X-ray that you're picturing. You get a three-dimensional color X-ray where different colors show you can put in false colors for the bone because calcium will have different X-ray energy. Now, the Royal Society wasn't happy with funding just the basic research, and so I had to persuade my colleagues at Canterbury. So yes, we first 5 years I had a grant to do medical imaging with these little detectors, and yeah, this looked really promising. And my colleagues finally decided, yeah, this medical imaging, they should go all in. And fortunately for New Zealand, the radiologists and the medical physics people and my colleagues, Phil and Anthony Butlers, were able to focus on something useful and applied that we could point to and convince the government that this spin-off research from the curiosity-driven research can be done, but it's going to take a while. Yeah. And people would laugh at me when I it might take 20 years to do this.
That spin-off is the game-changing CT scanning company Mars Bioimaging.
Over that first 5 years, when I held the grant, then Canterbury was able to take over the grant with MBIE funding. Mm-hmm. And they were granted millions of dollars to help, because apparently the technology idea and the medical imaging company idea struck a chord with the funding agency, more so than the Higgs boson, which did win the Nobel Prize, by the way. I'll just say that for Peter Higgs. So I think New Zealand has a lot of good vibes built up with the CERN laboratory, because we were able to come in, give them a new perspective, a biological perspective, which is what New Zealand's strength is, give them a New Zealand perspective on their technology. And that was take their technology and apply it to something biological, like X-ray imaging. But I think it really came down to the medical use. That really won the day. And so all the effort went into the medical end of it.
So here we are, sitting in your office with a fabulous view over Auckland City and Sky Tower.
Yes. Don't tell the VC that I have probably the better office and the better view, I think.
I know. But being so far away from CERN and the rest of the world, really, does that make any difference to your work?
It makes a practical difference in the sense that when I meet with my analysis groups, or when I meet with the Analysis Review Committee, the ARC, the ARC, talking about Nihar's latest paper, we have to meet at a time that works in India, United States, New Zealand, and Geneva. And so we'd meet from 12 to 2 in the morning, or 1 to 3 o'clock in the morning here. And that would just be somebody just coming into work on one side of the world, somebody in the middle of the day on the other side of the world. But New Zealand, being New Zealand, we would always be 1, 2, 3 o'clock in the morning. So there's that very real practical problem. And going to conferences, we've got to travel much farther if we want to visit. So I feel I probably haven't been able to keep up as much as I should have, or as I could have, if I did have a fundamental research money travel grant. The applied research money is great because it helped get us the medical imaging company and helped gave us access to the raw data. But the basic research money, which I never won, I've never won any of these Marsden Fund grants, over 20 plus applications. Yes, it just, I think 3 times I made it into the finals, but never had a winning proposal, which is kind of ironic, I think, since it's a Nobel Prize winning experiment, but that's another issue.
Do you have a goal, something that you really want to achieve in your lifetime with this project?
I just want to keep digging. I just want to be around to see this continuous advance, the continuous change and exchange of ideas with people around the world. I just love doing that, and that's why I'm at a university.
In exploration, there needs to be the set of people who have no rules, and they are going into the frontier.
That's a documentary called Particle Fever.
I've never heard of a moment in history where an entire field is hinging on a single event. The Large Hadron Collider, the biggest machine ever built, is finally going to turn on.
It follows 6 scientists working on the Large Hadron Collider that led to the discovery of the Higgs boson. It's otherwise called the God particle, and it's a term David hates.
I try to keep my science apart from my faith, and you can have both, and I do. But a God particle, from looking at the public perspective, it looks like somehow religion has infiltrated physics. And yes, some people would celebrate that, and other people would say, no, we can't celebrate that. They're completely different. I'm happy calling it the Higgs boson. That's my way of looking at it. I have a scientific lifetime, and I have a religious faith. And I don't know how God works in the universe. Maybe God does create Higgs particles so that human beings can exist, but I feel maybe we're not that special, and maybe Higgs bosons naturally appear. So let's go with that safe thing that we can actually observe in the laboratory.
Now, this is a little bit outside, well, this is very much outside your sphere, but it's about space.
I'll do my best.
Yes. The all-women trip to space with Katy Perry.
Yesterday was a big day in American history. A group of women finally met society's expectations to weigh 0 pounds.
But wait, I'm just wondering, which side is more willing to endure hardship for the glory of their nation? The one that's been around for thousands of years, or the one that's sending Katy Perry to space?
Is this good for space science?
I was talking about this with my wife, Liz, this morning. This Blue Amazon, was designed to take space travel, but it's going to be for tremendously privileged people to be able to afford to do this. You and I aren't going to be able to do this. And it's kind of, well, it's a little embarrassing that it took this long to get an all-female cosmonaut astronaut crew together, because we've been traveling in space since the 1960s. And as long as it gets people excited, as long as it gets young women, young girls excited about science, I'm all for it. I've got no problem with that whatsoever. I'd much rather have these excited women come and work in nuclear and particle physics, because here we have things that will last you a lifetime. You can do things with your hands and with your brain, and we want you to work for us.
And finally, a message to the government about why funding science pays off in so many ways.
I would just like to say that I think my colleague, Anthony Butler, will be traveling to Wellington to talk to the government about how important it is to do fundamental research because of the medical imaging company that Anthony and Phil were able to come together with and produce out of New Zealand. New Zealand, we are advancing. We're a spacefaring nation now, for example. We're going to crack the world medical imaging market. We have started a plasma energy research. These things happen not out of a vacuum. They happen out of fundamental science. And even if the title of the paper, the funding request, makes no sense to practical life, there will be eventually something that impacts the lives of the people who pay for that fundamental research. And we have hard evidence to show with these different companies coming out of New Zealand. And I'm very proud of that. And I'm just glad that University of Auckland saw fit to offer this dreamer a way to take part in his search in fundamental physics of the universe.
That's it for today. The Detail is a newsroom production supported by RNZ and NZ On Air. This episode was produced by Gwen McClure and engineered by Steve Burridge. Thanks to David Krofcheck. I'm Sharon Brett-Kelly. Ka kite.